Okay, good afternoon everyone. So we are at the tail end of this chapter 9. Right, so what we have done so far is we observed things about bricks. Some of these we already observed in chapter 8, by the way. None of the observations we have made about bricks so far have really been difficult. Once you know chapter 8 content, it has basically all been just corollaries. And yesterday we proved monotonicity, which is not about bricks. Of course, bricks is the interesting case, the base case, but then the induction goes through for both removable edges and removable doubletons. In the case of removable doubletons, the induction did not just go through, we resorted to the ELP theorem in order to make it work. Right? So all that is done. What remains is proving the existence of a removable edge in bricks. Of course, not all bricks, you can already see, K4 and prism do not have any removable edges. Let us recall that we have already observed something weaker. We know that every brick has at least delta max degree, pairwise mutually exclusive removable classes. Right? And in fact, the way we observed this is we forgot about bricks. We went to a matching code graph. We took a vertex of degree D and we just asked some questions in the locality of that vertex, the edges incident at that vertex, and we observed that if the degree of the vertex is D, then the graph has D pairwise mutually exclusive minimal classes. Right? So therefore you can take a vertex of maximum degree and you will get delta such classes. And in the case of bricks, minimal classes are removable classes. Right? Minimal classes of cardinality 1 or 2, and therefore when you delete the 1 or 2 edges, your graph will still be connected because some bricks are 3 connected. Right? So that is how we got this consequence that there are at least so many removable classes. But we know removable classes are of two types. Either they are removable edges, sometimes I call them singletons, you can blame Shalu for that, or removable doubletons. Right? So these are the two types of removable classes we have. But it would be nice if we could get, I think I discussed this earlier briefly, I'll just mention it again. If I delete a removable doubleton, it's kind of good news because I get a bipartite matching code graph in the case of a brick, which is great, but because bipartite graphs are nice, but it doesn't help you to prove things by induction, by the way, because now you deleted 2 edges from a brick and now you have a bipartite matching code graph. You don't have a smaller brick. That's one issue. And the other issue is, removable doubletons may not be there to begin with, which is in some sense good because then you know there is a removable edge. If there is no removable doubleton, then definitely there is a removable edge. Go ahead.
Did we prove that the graph you get when you delete these edges is matching cover? In general, if they are not bricks, they may be bipartite graphs that are not necessarily matching.
Oh, we are deleting removable doubleton.
Oh.
It's matching cover. Yeah. We are not deleting just a doubleton, equivalence class of cardinality 2. Yeah. So we have a matching code graph, that's not an issue. The only issue is removable doubleton will take you to a bipartite matching code graph. Then you won't be able to prove things by induction in the case of bricks. At least it is not immediately clear how you will recover a brick from the bipartite matching code graph. The bipartite matching code graph may be very far away from being a brick. That is if you want to prove things by induction. If you want to prove things by induction, in some sense, it is better to delete a removable edge. But even that's not great, because after deleting the edge, as per our proofs yesterday, the number of bricks in G minus E could be very large. So you deleted one edge from a brick, and now you have a matching code graph with 100 bricks. That doesn't help either. What would help is deleting an edge that is B invariant that we defined yesterday. You have one brick and bunch of braces, and you somehow shave off the braces, and now you have just one brick. So we are getting there. But before we prove the existence of a B-unit edge, which we will not in this course, that is done in part 2 of the book. I don't know when that will happen. Right? What we will do is we'll prove a weaker statement. There is always a removable edge in any brick except K4 and prism. Right? So that's the theorem we are going to prove. Every simple brick, well, if it is not simple, anyways, there is a removable edge. I'm still deciding whether I need simple or not. Let's see. Every simple brick has at least delta minus 2, which is at least 1. Removable edges. In fact, you can get these to be, I can pick a vertex of degree delta. Yeah, I think you can also get them to be mutually exclusive. We'll discuss that later. I'll just say for now, removable edges. Yeah, this is what we'll prove. Let's see, 9.14. Did I remove K4 in prism? Distinct from K4 in prism. Yeah. This was first proved for at least one. It was proved by Lovas. I believe in the 1983 paper, but I'm not sure. Yeah, I think it's 1983. Every simple brick has at least one removable edge, except for K4 in prism. Yeah. Okay. So let's see how we would get here. We know that there are at least so many pairwise mutually exclusive removable classes, right? So I look at a vertex of max degree. I don't need to draw these. I look at some vertex of max degree. Each of the edges incident at that vertex will give me a minimal class induced by that edge. And these, in the case of this vertex, I've drawn 5 edges. So I'll get 5 pairwise mutually exclusive minimal classes in the graph. Right? These will be removable classes because my graph is a brick. If any of them is a removable edge, then I have at least one removable edge and I'm kind of happy. That's the weakest statement we are trying to prove. What if all of them are actually doubletons? If all of them are removable doubletons, then we need to do something. Right? So in that case, in this graph, you would have 5 pairwise mutually exclusive removable doubletons. If there was a vertex of degree 5, you'd get 5 such things. Turns out this is not possible. In fact, it turns out that you can't even have 3 unless the graph is K4 or prism. This is what we'll prove. One of the things we'll prove is the approach is to prove a much stronger statement that the moment you have 3 pairwise mutually exclusive removable doubletons in a simple brick, the graph is either K4 or prism. K4 and prism are the only simple bricks that have 3 or more pairwise mutually exclusive removable doubletons. This is what we'll prove. If we prove this, then we are done. Yeah, you all agree? Because then out of the 5 at this vertex, induced by this vertex, at most 3 could be problematic. The other 2 are definitely not problematic. In fact, because it is only K4 in prism, you won't even have 3 problematic ones. You will actually get at most 2 problematic ones, and you will get 3 removable edges. Right? But anyways, what could happen is the vertex could have degree exactly 3, in which case 2 could be problematic, and I will get only 1 removable edge. Right? Anyway, so this is what we will prove, and I hope you all agree that once we prove this, we are done with this. That's the point. In fact, we will get something stronger. We will get delta minus 2 pairwise mutually exclusive removable edges. But I'm not going to write it down. Because I'm using this approach, I can just take a vertex with maximum degree, and now I can use all this, and I will get delta minus 2 pairwise mutually exclusive removable edges. But I'm not going to write that in the statement. I'm just saying delta minus 2 removable edges. Yeah? All good? Yeah.
I was thinking of something stronger, but then I realized like this proof uses something. I was thinking maybe we can say every vertex has a removable edge adjacent to it.
Oh.
But then I realized this goes into other vertices.
Oh yeah. Oh yeah. In fact, that is a good point. So, I mean, for example, the bicon. The bicon has exactly 3 removable classes, and only one of those 3 is a removable edge. The only removable edge in bicon is this fellow. This is a removable doubleton, and by symmetry, this is a removable doubleton. Yeah, and in fact, yeah, so let me see what is true. Having one at each vertex is too much to ask for. What you can ask for is, can you prove the existence of 2 removable edges? Well, not in the bicon. Bicon is only 1 removable edge. I believe one of your assignment exercises, for group 3 at least, asks you to prove the existence of 2 removable edges in every brick except K4, prism and bicon. I think that is the last exercise in the assignment, if I remember correctly. Yeah. So that is true. If you exclude the bicon, then you can get 2. And even in that case, we don't know how to get 2 non-adjacent ones. They could be adjacent. Yeah, I think that is not known. But yeah, I think anyways, Lucchesi Murthy have notes where they discuss all these things. So, yeah. Okay. So yeah, proving the existence of removable edges in bricks is in general pretty difficult. And it gets much harder when you go to special types of removable edges, such as being mirrored edges, and then you go even more special types, thin and strictly thin edges, which I have not discussed yet. We'll probably discuss at some point. Yeah. Okay, good. Yeah, unlike braces, braces are nice. Every edge is removable. But very good. Okay, anyway, so this is the situation in life. Okay, any other questions, concerns? Okay, is the general approach clear? The statement we will prove is this statement. In fact, we will prove something slightly stronger than this. We will drop the word removable. We'll just focus on doubletons. By doubleton, I mean pair of mutually dependent edges that need not be removable, as we have seen in that 12 vertex graph that we constructed a few lectures ago. We took 2 copies of K33, we added 3 edges like this, and we added 2 more edges. Yeah, everybody remembers that? K33, K33 here. This fellow. This fellow is a brick once you add the other 18 edges. And alpha beta is a doubleton that is not removable. I'm using the word doubleton, but so in this lecture by doubleton I mean, typically I don't use this, but today it will simplify my life. By doubleton I mean an equivalence class. In the case of bricks, we know that equivalence classes, minimal or not, are of cardinality 1 or 2. Right? So therefore, by doubleton I mean today an equivalence class of cardinality 2 that is not necessarily removable. That is not necessarily minimal. Because if it is minimal, it will be removable. We know that in a brick. Yeah? So this is an example of a so-called doubleton. Yeah. So what we will prove is that we won't need the removable assumption. If you have a simple brick with 3 pairwise mutually exclusive equivalence classes of cardinality 2, then the graph is either K4 or prism. Yeah. You may say, why do we need simple? Let's address that. I suppose everybody can see the 3 doubletons. In this case, they happen to be removable. Yeah, you all can see the 3 removable doubletons. Pick one edge from the triangle and the corresponding edge from the other triangle. Yeah. What I can do is I can also add this edge. They are still removable doubletons. So that is why we need simple here. If I don't put simple, then I have to say that in the case of prism, you can add as many multiple edges here as you like. And it doesn't change the property. Yeah. In the case of K4, if you add a multiple edge, you will simply destroy one of the removable doubletons. Right? So K4 is fine, but in the case of prism, you need to allow these edges to be multiplicity greater than 1, at least 1. Right? So that is why we are going to put simple. Is that okay? Okay. Questions, concerns? Is the general idea clear? What we are trying to do? This is the statement we are going to prove. Okay. So, we have 3 pairwise mutually exclusive doubletons. So let's consider a graph that has this property. Consider a simple brick with this property. Yeah? Our goal is to show that G is either K4 or prism. Is that fine? So what we will do first, instead of focusing on all 3, let's consider 2. Supposing I have 2 mutually exclusive doubletons in a brick. Can we use that to get some information about the graph? If we can get some information for 2 such doubletons, then we can now apply that information to all pairs and maybe get more information. So that's the idea. Okay. So what we'll first do is we'll focus on the case of a simple brick that has 2 mutually exclusive doubletons. Okay, so instead of G being this, let me just define G slightly weaker. A simple brick I would like you to not pay too much attention to simple. We will see when it actually comes up. Don't think too much about simple, it doesn't really matter. Consider a brick that has a pair Q1, Q2 of doubletons. Yeah, I'm not a big fan of this word. Okay, I'm just going to use it today. Doubleton is like singleton. What's a singleton? It doesn't mean anything. Okay, let us try to analyze this situation. Right? I have not made any assumptions whether these are mutually exclusive or not. No assumptions right now. Let's just try to understand what two doubletons give us in a brick. We have already observed that their union is a four-cut. We have already observed that their union is a four-cut. We'll go through that thing again. Right? So we know that a pair of mutually dependent edges in a brick looks like this. When you delete the two edges, you get a bipartite matchable connected graph. Need not be matching covered. Matching covered would mean removable doubleton, but that is not necessary. This is the example where it is not the case. So our graph looks like this. This is, let me give names. QI is EI, FI. Yeah, so my edge EI has both ends in, let's say I'll draw for 1. My edge E1 has both ends in A1. My edge F1 has both ends in B1. And when I delete both edges, I have a bipartite graph with colored classes A1 and B1. Let's make one more drawing. So this is with respect to Q2. I have A2. I have B2. The edge E2 has both ends here, and the edge F2 has both ends here. Yeah. And this is a cut. This is a cut. Their symmetric difference Q1 union Q2 is a cut. Yeah. Let's get more information. Yeah. So we'll make our standard drawing of two cuts. Let's say this is my pink cut, this is my blue cut. Yeah. So let me make pink horizontal here, and let me make, whatever. Okay. These are my two cuts. Yeah. The two sides of the pink cut are A1 and B1. And the two sides of the two shores of the blue cut are A2 and B2. Yep. So I want you all to translate these drawings into this one. Figure out where the edges E1, E2, F1, F2 are. See if you can complete this. Yeah. And I also want you to think separately about the following. We have seen this in SGT. If I give you a graph with two cuts, G is some graph and partial of X and partial of Y are cuts. Why exactly is this fellow a cut? Right? I mean, of course, this is kindergarten, but let's not forget kindergarten. Right? Yeah. At this stage, it is kindergarten, I suppose, but yeah, it still has important lessons. Every time I upload a lecture on YouTube, it asks me, I have to select yes, it's made for kids, no, it's not made for kids. It's always tricky. I'm almost tempted to be like, yes, it is. But then I'm like, no, maybe not. I'll just label the 4 quadrants. This is A1 intersection A2. This is A2. Yeah, so B1 intersection A2. B1 intersection B2. And this is right. So if you are struggling to figure out the location of the 4 edges, try to first figure out this. Why is this a cut? What are the shores of this cut? Right? If it is a cut, it should have shores. Okay, so the point is, this is exactly partial of x symmetric difference y. Right, so therefore, what you are looking at is simply the cut corresponding to this set. And this set is exactly, if I think of my x as A1 and my y as A2, then I simply get this as the shore of the cut. These two sets, they comprise one shore of the cut, and these two sets, they comprise the other shore of the cut. Yeah? And the only 4 edges I should get in this cut are these 4 edges, E1, E2, F1, F2. Right? So these are the only 4 edges that go from this shore to this shore. One diagonal to the other diagonal. Right? Observe that E1 has both ends in A1. E1 has both ends in A1. However, E1 has one end in A2 and the other end in B2. Yeah? This is the same graph drawn differently, right? So both ends of E1 are in A1, whereas one end is in A2 and the other end is in B2. Both ends are in A1, one in B2, one in A2. This is E1. Yeah. F1 has both ends in B1, but in the other graph, in the other drawing, one end is in this set A2 and the other end is B2. So F1 is here. Yeah. E2 has both ends in A2, And now you can see that it's all symmetric, very nice. This is E2 and this is F2. Where are all the other edges of this graph in this drawing? Think about that. So we know these 4 edges, they look like this. What about all the other edges? Where are they? Alright, so looks like everybody has convinced themselves that all the other edges that I have not drawn here, they go from here to here or from here to here. Every other edge in the graph is of this type, either the first type or the second type. There's no real difference between the two. At this point, everything is symmetric. Yeah. Okay. So what we'll do is, this doesn't look very nice. Because I have to imagine the two shores. One shore is this for this forecut and the other shore is this. What we'll do is we will try to put both shores on the same side. We'll make a different drawing. Yeah. Okay. We'll make a slightly different drawing by putting both shores on the same side. It has its advantages. So let's do that. A1 intersection A2. Okay, A1 is on the top here, fine. A1 intersection A2 is one part of this shore. The other part of this shore is B1 intersection B2. Don't worry about the boxes being equicardinal in my figure, or at least looking equicardinal. That's okay. I'm not saying anything about the cardinalities of these boxes. Okay, so try to liberate yourself from the geometry. So this is one shore, and the other shore is A1 intersection B2. I will put A1 intersection B2 on the top. And A2 intersection B1. Yeah? Yeah, I've just drawn the 4 sets like this. The advantage of this is that now it actually looks like a cut. Here somehow the 4 edges don't look like a standard drawing of the cut. Now it actually looks like a cut. Left side is one shore, right side is the other shore. Yeah? Okay? Now let's complete the 4 edges. Can we do that? That should be easy, right? A1 goes from A1 intersection A2 to A1 intersection B2. So A1 goes like this. This is E1. F1 will go like this. E2 goes from A1 intersection A2 to A2 intersection B1. And F2 goes like this. This looks more like a cut, yeah? All good? This is our graph. All the other edges, now it's easier to see. All the other edges, now you don't have to do that funny thing. All the other edges are here. Yeah? This probably became this, and this became this. All the other edges are looking like this. Yeah? This also shows the bipartition quite clearly when I remove all the 4 edges. Or actually, if you remove any 2 edges, E1, F1 and or E2, F2, you can actually see the bipartition for both of those graphs, for both of those bipartite graphs. Right? In one case, the bipartition is what you see. If you delete E1 and F1, this is one part, this is the other part. Whereas if you delete E2 and F2, then you see this is one part and this is the other part. Okay? Questions, concerns? All good? Yeah? Okay. Now we'll try to get more information. So far we have not used the hypothesis that Q1 and Q2 are mutually exclusive. We haven't used that so far. Yeah? And in fact, we still won't. We will still try to not use that hypothesis. But let's observe something. If I take a perfect matching containing Q1, Q1 is E1 F1. Either it will contain Q2, both edges, or it will not contain Q2 at all. It will not intersect with Q2. You all agree? Because Q2 is an equivalence class. Yeah? So any perfect matching will either contain both Q1 and Q2, or it will contain exactly one of them and have empty intersection with the other, or it will have empty intersection with both of them. These are the possibilities in life. Yeah? Now I want you all to do some counting. Can you all think about the perfect matchings of the graph G? This is the new drawing I want you to think about. Think about this drawing and see if you can get some more information about the cardinalities of these boxes with respect to each other in some way. Yeah? Think about it. What can you say about the cardinalities of these boxes? There is one more subtle point I want to make. You may imagine, you may think that there are 8 distinct vertices. We haven't proved that. It is possible that this is the same as this. So keep that in mind. We don't know whether these are adjacent or not. Of course, if E2 and E1 are adjacent, then it is clear that they are actually mutually exclusive. Right? If 2 edges are adjacent, then of course they are mutually exclusive, and the corresponding equivalence class is also mutually exclusive. So there is something going on there. But for now we don't know whether they are adjacent or not. Right? Okay? So I want you all to think about the cardinalities of these boxes. I mean relative cardinalities, not absolute. use perfect matchings and counting. There are multiple ways to count. As always. Yeah, I'll put this in brackets. Apparently this is not necessary. I mean, I tend to use it because I tend to not think about too many other things in life apart from perfect matchings. But yeah, there are ways to avoid it. If you're stuck because of some technicalities, just make an assumption that allows you to get rid of those technicalities. So there are multiple ways to prove that this has the same cardinality as this, and likewise this has the same cardinality as this. Okay. One standard way is to just consider perfect matchings. Consider a perfect matching. So I think I like Manoj's way of eliminating cases because they are distinct equivalence classes Q1 and Q2. There has to be a perfect matching that contains one of them but not the other. If every perfect matching contains both of them, then they should be the same equivalence class, no? Right? So because they are distinct equivalence classes, there is a perfect matching that contains one of them but not the other. That actually makes life much easier. So take a perfect matching containing E2F2 but not E1F1. So I have used these two edges, but I am not using these two edges. Well, therefore all these vertices have to match here, all these have to match here, apart from those four ends of E2 and F2. Therefore they are equicardinal. Now you put back the two vertices, they are still equicardinal. So that is one way to finish it. Of course, even if you don't make that observation, you can just consider all possibilities. Perfect matching containing Q1 and Q2, do the counting. Perfect matching containing one of them, and perfect matching containing neither of them. All cases you can do the counting and you will arrive at the same conclusion. It's one of those classic examples of all roads leading to Rome. Well, because they should lead to Rome anyways. Maybe Chennai in this case. Yeah. So, right, so that's one way to do it. But the other way that I thought was very cool, that I had never seen before, given my limitation of perfect matching thinking, observe that cardinality of A1 is equal to cardinality of B1. That we know by patterned matchable graph. So cardinality of A1 is equal to cardinality of B1. Cardinality of A2 is equal to cardinality of B2. Yeah. Now, so that means if I have, let's make it more concrete. So there are n over 2 vertices here, n over 2 vertices on this side, n over 2 on this side, n over 2 on this side. Yeah. Observe that to get to this set, I can simply take this set and remove this. Or to get to this set, I can take this set and remove this. In both cases, I am removing the same quantity from n over 2. Therefore, these two are equal. Right? Is that the argument? So, therefore, these two are equal. And the same argument, these two are also equal. So, no perfect matchings. This was the argument Amit had, and I think eventually Santosh had the same argument. So yeah, this is one way to do it, and no perfect matchings are used here. Yeah, I had never thought about this. Nice.
We are using the fact that G minus Q1 is matchable.
We are using the fact that G minus Q1 is bipartite matchable graph. Yeah, so for A1 is equal to B1. Yeah, that part we are using here. Right, true. But yeah. Cool. So there are many ways to conclude that these two are equicardinal and these two are equicardinal. Let's just write it down. A1 intersection A2 has the same cardinality as B1 intersection B2, and likewise A1 intersection B2 has the same cardinality as A2 intersection B1. Yeah? All good so far? At this point, thus far, we have not used mutual exclusive or anything. We are just taking two doubletons and trying to get inferences from that regarding the structure of the graph. Right? And this is so far where we have reached. Okay. Until now, we have not concluded anything about these 8 vertices. Whether they are 8 distinct vertices or are some of them actually the same vertex, we don't know. Right? Definitely 4 distinct vertices are there, because 4 distinct I can see here, but we don't know more than that. Alright. So, either Q1 union Q2 is a matching, in which case you have 8 distinct vertices. Yeah, either Q1 union Q2 is a matching. In this case, we will prove that Q1 union Q2 extends to a perfect matching of the whole graph. If Q1 union Q2 is a matching, these are 4 pairwise non-adjacent edges, then we will prove that Q1 union Q2 extends to a perfect matching. Therefore, Q1 and Q2 are not mutually exclusive. Okay, this is what we'll prove next. And I'll give it to you, all of you, to prove it. So, here is the next claim. If Q1 union Q2 is a matching, then Q1 union Q2 extends to a perfect matching of G. Thus, Q1 and Q2 are not mutually exclusive. Once we prove this, we will use the contrapositive of this to make more progress. If they are mutually exclusive, then yeah. So try to prove this. Assume that Q1 union Q2 is a matching. So my drawing is actually an honest drawing. 8 distinct vertices. See if in this case you can prove that these 4 edges extend to a perfect matching of the whole graph. I want to finish this proof today. Let's see. And if you are really struggling, you can ask me for a hint. Okay, try it, try it. I'll label all the 8 vertices. Maybe that will help. S, T, U, V, W, X, Y, Z. These are 8 distinct vertices. Maybe I'll give one hint to everybody. Yeah, so maybe I'll just give one hint. Is you should use, well, I don't know other ways of doing it. And I think if you remove the statement brick, if you remove the hypothesis brick, probably you can find counterexamples to this statement. But I'm not sure, I don't have a counterexample off the top of my head. So you want to use the property that the graph is a brick. And well, there are mainly two definitions, free of non-trivial type cuts. It's not very clear how you'll use that. So therefore you go to the other definition, bicritical, three connected. And three connected is also not very clear how to use that. Bicriticality is what you want. So what you really need to use, at least one way that I know how to complete the proof, is by using bicriticality. Right? And now you have to figure out which pair to operate on. Right? The point is, if two vertices are adjacent, that is not a very useful pair, because anyways you know graph is matching covered, so adjacent will not help you. And in some sense, we know that when we delete these two edges, for example E1 and F1, we have a bipartite matchable graph. Let's see. Yeah, I was trying to make some statement, but I'm not sure anymore. Anyways, so bicriticality is what you want to use, but there are multiple pairs to operate on. So try to see if you can find a pair that actually helps you in making progress. So let's do one thing. Let's try to reverse engineer things a bit. Right? What are we trying to do? We are trying to get a perfect matching containing all these edges. Just draw one. Draw a perfect matching containing all these edges and see what it requires you to prove. Supposing I want a perfect matching containing all these edges, so this is used, this is used, this is used, this is used. All of these are used. So what does the rest of this matching look like? Supposing, let me put some vertices here. 1, 2, 3, 1, 2, 3, 1, 2, 1, 2. Supposing there is a perfect matching using all these 4 edges, then what does it look like? You take those edges and you take these edges. I don't know, some perfect matching like this. This is what it will look like up to permuting the vertices. You all agree? So you want to show that this graph, after deleting these 4 vertices, has a perfect matching. Do you all agree? I'm just trying to go in the reverse direction. If there is a perfect matching containing all 4 edges, it has to look like this. So it is if and only if this graph, this component minus S, T, W and X has a perfect matching. Likewise, this component minus U, V, Y, Z has a perfect matching. If you can prove that, then you're done. You see my point? Let me just write down. Supposing this is my, I don't know, J and this is my K. These are the 2 components after deleting Q1 and Q2. Okay? It's a bond. It's not only a 4 cut. We'll actually get connected by peptide 2 graphs. So anyways, that's not the point. This is my J, this is my K. What we want is J minus S minus T minus W minus X has a perfect matching, and K minus U, V, Y, Z both are matchable. This is what you want to prove. This is equivalent to saying that there is a perfect matching containing all 4 edges. You all agree? It's the same statement. Now see if you can make progress. And observe that these 2 are actually symmetric. If you can show that one of these 2 is matchable, then the other is also matchable. There's no difference between them. This might help you to figure out a good pair of vertices to delete. Okay, so I will give you one more hint. Focus on just this. Don't worry about everything else. Just focus on this graph. See if you can show that this graph is matchable. If you can show that this graph is matchable, then by the same argument this graph is matchable. You take the two perfect matchings, include Q1 union Q2, you are done. So that's what you want to focus on. J, the left hand side, you delete all the four vertices. That graph should have a perfect matching. The original graph is bicritical. Now that should give you some hint on what pairs to try.
Suggests that you should try some of these possibilities. Supposing you try these two, what will the perfect matching look like? Supposing I delete these two, so now what will my perfect matching look like? Yeah, so what do you get? Think about G minus S minus T.
So what I'm suggesting is, this should kind of help us in guessing what possibilities to try. Consider G minus S minus T. G minus S minus T has a perfect matching because G is bicritical. Now try to observe what this perfect matching looks like. You have 3 vertices here and 5 over here. Yeah? So what can we say about this perfect matching? So M is a perfect matching. Let me call it M1. M1 is a perfect matching of G minus S minus T. So what can we say about, so because I deleted S and T, edges E1 and E2 are gone. Yeah? What can we say about edges F1 and F2? Can we say something? They are both used. They are both used in this perfect matching. Let me use another color. So in this perfect matching of this graph, we must use F1 and we must use F2. Observe that these three vertices are indeed matched to three vertices here. Therefore, J minus S minus T minus W minus X has a perfect matching. Right? So do you agree that this graph has a perfect matching? I just took the restriction to the left side. If I take the restriction to the left side, I get exactly these three edges. I get a perfect matching of this graph. So this graph is matchable. By the same argument, this graph is matchable. Not the same pair, the same argument. By a similar argument, by an analogous argument, this graph also is matchable after deleting these four vertices. Take the union of those two perfect matchings and include Q1 and Q2. You have a perfect matching of the whole graph G containing Q1 and Q2. The power of bicriticality. Right? So this works. So what we have just proved is that if this is a matching, then this extends to a perfect matching of the whole graph G, and therefore the two Q1 and Q2 are not mutually exclusive. Therefore, if Q1 and Q2 are mutually exclusive, then Q1 union Q2 should not be a matching. There is a pair of adjacent edges. Do you all agree? Contrapositive, right? Okay. Let's make some more progress. We are not taking any break today. So at this point we will assume that Q1 and Q2 are mutually exclusive. Okay, until now we did not assume this. Until now we just made some observations. So now new assumption. Assume that Q1 and Q2 are mutually exclusive. Yeah? That means that Q1 union Q2 is not a matching. There is a common end. So let me just make the same drawing. Yeah? I'm going to assume without loss of generality that let's see, blue and pink. Blue is my E1 and F1. So let me draw E1 like this. This is E1, and let me make E1 and E2 adjacent. Is that okay? Without loss of generality, I will make E1 into adjacent. Maybe I'll put white vertices. E1 and E2 are adjacent. Okay? The other edges I am not going to draw because I don't know whether they are adjacent or not. Is that okay? E1 and E2 are adjacent, and I have put a common end over here. I would like to convince you that if this happens, then actually something much more than this should happen. Okay? If this happens, here is what we will do. I want you to convince yourself, maybe try it. If this happens, then not only are E1 and E2 adjacent, actually F1 and F2 are also going to be adjacent. And these two vertices are going to be degree 3 vertices, and this will be the whole color class. This will be the whole set A1 intersection A2, and this will be the whole set B1 intersection B2. This will be A1 intersection A2, and this will be B1 intersection B2. Okay, so this is what I want to convince you, that if E1 and E2 are adjacent, then actually the other two edges F1 and F2 are also adjacent. The common ends of these two edges are degree 3 vertices. They are actually neighbors with each other. There is actually an edge over here, call it H, another edge. And in fact, the whole set A1 intersection A2 is just this vertex, and B1 intersection B2 is just this vertex. Okay, but we are not there yet. We are in this drawing. Okay, we want to get to this drawing. Is the idea clear? Okay, let's suppose I put some vertices here. I put 4 vertices here, 4 vertices here. Yeah, let me put 5 here. 1, 2, 3, 4, 5. Yeah, everybody with me? I claim that there is a non-trivial tight cut in this drawing. I've put some vertices here. I want to show that this box is only one vertex. I have put more than one vertex. I claim that there is a non-trivial tight cut here. There are probably multiple ways to finish the proof here, but yeah, one way I can see is I can show you a non-trivial tight cut. I have not drawn the other two edges, E2 and F2. We can probably draw them somewhat vaguely. E1, E2 is fine. F2 and F1 I have not drawn. F2 is a pink color edge that goes like this, and F1 is a blue colored edge that goes like this. This is F1 and this is F2. In the interest of time, I will give you a hint. If you see a stable set of cardinality k, whose neighborhood is exactly k plus 1, that is the shore of a tight cut. In any matching covered graph, if there is a stable set of cardinality k, whose neighborhood is of cardinality k plus 1, then those two sets, the set and its neighborhood, they comprise the shore of a tight cut. I did not say non-trivial. The other side could be not trivial. I don't know. So can you see a set whose neighborhood is exactly one more than its own cardinality? This is S equal to T. You see a set whose cardinality, whose neighborhood is exactly one more than its own cardinality. Yeah, you all see it? It is all the vertices in A1 intersection A2 minus the common end. Look at this set. Its entire neighborhood is this set. Yeah? Therefore, this is the shore of a tight cut. It is non-trivial if there is at least one vertex here, and anyways the other side is non-trivial because there are at least two vertices here. So if there is at least one vertex here, then this is a non-trivial tight cut. Contradiction. Therefore there are no vertices here. Therefore we have already reached somewhere. That means there is only one vertex here. All of this is cancelled out. Yeah, there is only one vertex here. Well, if there is only one vertex here, there is only one vertex here. Yeah. So that fellow is the common end of F1 and F2. Right? Because F1 and F2 both have their ends in this set. There's only one vertex. So that is a common end of f1 and f2. That is the fellow w equal to x. This is w equal to x. Yeah? But there has to be another edge here. It's a brick. There has to be another edge here. Well, that means this is a degree 3 vertex and this is a degree 3 vertex, because if I remove all the 4 edges, I am disconnecting the graph into, yeah, thank you. Alright, so welcome back. So the point is, what did we prove? We proved that if these 4 edges, they comprise a matching, then Q1 union Q2, Q1 and Q2 are not mutually exclusive. Yeah. So if they are mutually exclusive, then actually they cannot be a matching. Q1 union Q2 cannot be a matching. 2 of the edges have a common end. Without loss of generality, we assumed E1 and E2 have a common end. Now, using the fact that this is a common end, we concluded that actually there is only one vertex in this entire set, A1 intersection A2. Therefore, there is only one vertex in B1 intersection B2. That vertex is the common end of F1 and F2. And now, using the fact that a brick has degree at least 3, we were able to conclude that these two vertices are actually neighbors of each other. And because this is a 4-cut, they don't have any other neighbors in life. Yeah, they are both degree 3 vertices. So what have we proved? We have proved that if a brick has a pair of mutually exclusive doubletons, then actually the doubletons are adjacent at 2 different points. E1 F1 and E2 F2 are my doubletons. Then E1 and E2 will have a common end. F1 and F2 will have a common end up to relabeling. And the 2 common ends will be degree 3 vertices of the graph that are actually adjacent to each other. This is called the H configuration. Right? I think we discussed in our last meeting, maybe Rahul and Santosh, right? So this is the H configuration. The H is going to be drawn sleeping. This is H configuration. They write it like H configuration. And E1 and E2 share a common end. F1 and F2 have a common end. And these 2 vertices are adjacent using some edge H, which is not E1, E2, F1, F2, and they are actually degree 3. You can start seeing K4 and prism are going to show up soon. We are only dealing with 2 mutually exclusive doubletons, but actually we have 3 mutually exclusive doubletons. So therefore we will be able to use this proposition for each pair, Q1, Q2, Q2, Q3 and Q1, Q3. And we will be able to actually conclude that the graph is either K4 or prism. This is a DIY for all of you. Right? What I will do is I will just tell you, this is basically what we proved today is lemma 9.12. Yeah. If two doubletons are mutually exclusive, then they must form the H configuration. Now you have 3 mutually exclusive doubletons. Conclude that the graph is K4 or prism. DIY. Yeah, and this we will complete next time. So yeah, questions, concerns, all good? Okay, let's conclude here because there's another class here, and we will continue on Monday. We will finish chapter 9 on Monday, and we will start on chapter 10. Yeah, thank you.